Okay, so redox means, or is a different way of describing reactions. So again, in grade 10, when we focus on single, double combustion as, the be all end all, that's just not true. So we looked at organic reactions and how they can be treated differently. And this is another case as well. And we're really going to do the very bare minimum. And so those of you that continue in engineering or science for like not healthcare, then you'll probably do a lot more with electrochemistry, because just like acid base reactions, which in grade 10 we called neutralization, are better described as proton transfer. Same with this. So this type of thinking for a reaction will actually work for many reactions that before in the past we would have said, you know what, we have to skip that. Like, for example, we do a little bit of explaining why the transition metals can have more than one charge, but not a lot. We talked a little bit about how some elements we would have said, like chlorine is -1, but you can see that it's got more than one charge underneath its symbol. So looking at a reaction and whether something gains electrons or loses electrons is a little bit better, because it will describe a wider variety of reactions. So some teachers will use the acronym, I guess, Leo says GER. Okay, so if something loses electrons, then we say that's oxidation. If it gains electrons, we say that's reduction. So in biology, then you say that reduction, gaining electrons, is actually also a gain of energy. So then when the cell is making ATP or whatever, that's when you would talk about redox. And so there is actually quite a complicated procedure for balancing redox reactions that we are not going to do. That's a university thing. Again, if you choose to continue in, more physical sciences as opposed to life sciences. So what you can do is look at how many electrons are gained in a reaction, how many are lost. You can use protons, which is hydrogen, to help balance it out. So it can get quite complicated for what we're going to do today. So they occur simultaneously. That means if something is considered to be reduced, then something else has to be oxidized. And when you get to the more physics side of things, you can write a half reaction. So in the booklet, I included a standard reduction table, which is just a little bit less cluttered than the one in your textbook. And tomorrow we're going to look at how to write these reactions as half reactions and then how to combine them, which is then essentially what electrochemistry is. Something loses electrons, something gains electrons, energy is transferred, and depending on the substances you have, you can make a battery. So if something loses and gains electrons, even a lemon can be used to make a battery to generate energy, a potato. In elementary school, if your teacher was sort of into STEM, or if you got to do STEM, sometimes they do stuff like that. Is a potato or lemon going to power your laptop? Probably not. So we have much fancier batteries with precious metals that are more expensive, but certainly the generation of energy in a spontaneous way is what electrochemistry is about. So there's different ways to think about whether something is losing or gaining electrons. Sometimes you can think of it like becoming more positive or becoming less negative. So we'll look at a bunch of different ways to figure it out. So one of the types of questions you're going to have to do is assigning oxidation numbers.
Pardon the interruption. Would teachers of all grade 10 classes please proceed to the cafeteria for the presentation now? Again, that's all grade 10 classes, to the cafeteria for our presentation now. Thank you.
So we're gonna, I think it's the next slide has some rules, and some of them you will already know. So there are substances And you can check on your periodic table, for example, oxygen is always -2. So then what you can do is look at a substance and use some of the rules and figure out what the unknown oxidation number is. So we're going to look at glucose, which is C6H12O6, MnO4 or potassium permanganate, or sorry, not potassium, just permanganate. Why is it MnO4 with a negative charge? So again, sort of looking at things that in the past we would have been like, here you go, just use this instead of telling you where it came from. So sometimes it is the ionic charge, but not always. And then we're going to figure out what will be oxidized and what will be reduced. And what we're going to do is some of the ideas you're already going to be familiar with. So for example, on the reduction table at the top is fluorine. So F for fun, fluorine is the most electronegative element, the most greedy for electrons, which means it's the most likely to be reduced. And then in the bottom is an alkali metal, which of course are very reactive, readily lose electrons, and then losing electrons, this is most likely to be oxidized. So we can use, so don't push out of your brain. Things that we have already done, we're just kind of taking it to the next step. Instead of just saying, look at the Roman numeral for manganese, which has 5 potential oxidation numbers, which one is it? And you can calculate it. Okay, so some of these rules are things that you already know. Anything that's in its elemental form is going to have an oxidation number of 0. So if you have sodium, which is a metal, all by itself, it's going to be 0. Most elements will not be tricky. Again, you just have to remember about the diatomics. Okay, so the diatomic elements, that is considered when they're gases to be their elemental state, which we've been doing forever and ever. Okay, so you, again, just think about things that we've done before when we did standard enthalpies of formation. You couldn't look up a value, say for nitrogen, because the chart didn't have it. It was 0, right? So all that stuff from before. If something already has a charge, then it's going to be equal to the oxidation number. So an ion has a charge. So say, I'll just continue with sodium. Okay, so the sodium atom is 0, but if it's aqueous, we would have written plus, right? It's in the first column. On the periodic table, it's an alkali metal. Its charge is +1. You can write +1, 1 plus. When it's 1, just like math, we don't often write that down. So in the past, we would have said the charge on the sodium ion is 1. So then the same thing is true for a monatomic ion with its oxidation number. So you might be like, yeah, obviously, Miss Todd, but again, so we would have said ionic charge is 1. So now we're just going to call it the oxidation number if you're trying to figure out which one's oxidized and which one's reduced. And this is more of like a procedural thing. So what we're going to do is we are going to write a really simple algebraic expression to solve for the unknown, just like you would have done, in grade 9 math. So if you have a compound, like say you had water, when you have a compound, whether you crisscross or not, what should the charge of the overall compound be? It's going to be 0. Okay, so then if you have a polyatomic ion, then its charge is -1. So some of your grade 10 teachers would have talked about the crisscross rule, the zero sum rule, that adding the charges together should give you 0. Oh, sorry, there it is. The polyatomic ion should have a charge equal to what it is. So these two are more like, this is what we're going to do, as opposed to a rule. So when you're asked to figure out what the oxidation number is, usually it's in situations where you couldn't have done it before. But when you're first doing this, then most of the time it's going to have a hydrogen or oxygen. So then you'll have one of the values and then you solve for the other one. So fluorine is always going to be -1. And if you use our periodic table, then you can check the number underneath the symbol. O, oxygen is always -2. There is an exception, but peroxides are so rare. Okay, so normally we're just going to use this. Same thing with hydrogen. We're going to use +1. In a rare case where it's actually the nonmetal in an ionic compound like sodium hydride, then it could be -1, but that's going to be, our special exception, which is not really what we're trying to do here. And then if you have a case where you have a molecular compound that doesn't have hydrogen or oxygen, which again is not as common as you would think, the more electronegative element is assigned an oxidation number equal to its ionic charge. And so in this case here, in this rare case, where you would be asked to do this kind of question, there's no hydrogen, no oxygen. So how do we check? The electronegativity table is on the back here. Phosphorus is 2.19, chlorine is 3.16. So since chlorine has a higher electronegativity, its charge is -1, and you can calculate phosphorus's. This is very rare for what we're going to do. Usually the compound will have one of these, and you solve for the other one. So let's see how that works. Okay, so carbon is a popular choice for a question that you have to answer because, of course, carbon is in the weird column of 4. So what do? So we looked at one way how to deal with it, like organic compounds. But what about something like this here, where you're asked for the oxidation number? Okay, so we are going to write a really simple algebraic equation and solve for the carbon, basically. Okay, so we have to remember so as I said, it sort of depends on your grade 10 experience. Some grade 10 teachers will, when you're first learning about the crisscross rule or doing the charge for the charges, they will actually get you to calculate the zero-sum rule. So what the making a compound with an overall charge of 0, which is considered to be stable. So that's one of the reasons we say that charges are crisscrossed. Why does that happen? So that the overall stability is greater as a compound. So then we're going to add whatever the oxidation number of carbon is, which we don't know, plus 4 hydrogens is equal to 0. So then if you know what hydrogen is, we can solve for carbon. And again, if you use our periodic table, you can check, is -4 a possibility for carbon? Yes. Okay, so you can look underneath. In a second, we're going to do manganese and MnO4. So manganese possible charge is 76432. So before you even start, you can take a look and say, okay, my number has to be one of those. So you can kind of check that you've done it right. And again, could I make up whatever I wanted to? I suppose. But we are going, we would like the questions to be as practical as possible. So this is just mathematically not subjective, like easy, a same answer every time way to figure out the oxidation number. Okay, so let's do MnO4. So as I said, manganese is a strange transition metal with 5 possible charges. So now when you have a polyatomic ion, use the charge that's given to you. Even if there was a nasty question and it didn't give you what the polyatomic ion was, remember there are some of them on the back of your periodic table to help you out. We can't have 2 unknowns, so we have to use the oxidation number for oxygen as -2. Okay, so manganese, which we don't know, we're going to do 4 times oxygen, which is -2, but this time it equals -1 because it's a polyatomic ion, it's not a compound. Sorry. Okay, so again, you can check. I look at manganese, there it is. 7 is a possible choice, so I'm probably right. Okay, so what happens if you have to do this sort of thinking in a reaction to decide if something is oxidized or reduced? So what we're going to do is really sort of essentially treat it like a number line. So if you have Leo, which is losing electrons, and electrons are negative, then if the number becomes more positive, which is technically increasing, then that's oxidation. So you can kind of think of it like a regular number line. So let's say you have this. We would consider more positive, we would call that increasing in math, okay? So if it increases, it's going to be oxidation. Or if you would prefer to think of it with the Leo, then your if you become more positive, then that is electrons losing negativeness. And then a decrease in oxidation number, which would be then more negative, we would consider that to be a decrease. But it's weird because gaining electrons, it doesn't like becoming more negative doesn't necessarily have a bad connotation in chemistry, but it does mean that the number is technically decreasing if you think about like a number line. And then it's becoming more negative or gaining electrons. Which is GR. Okay, so as cheesy, some teachers will even go so far as to say Leo the lion says GR, whatever, it actually works. Okay, so this is, I don't know why some of them are different colors, so that's okay. So sometimes you'll be given a reaction and you have to identify oxidation and reduction. So again, in the simplest type of problems, it has to occur, something is oxidized and something is reduced. And then in this case, we have carbon, we have hydrogen, and we have oxygen. So oxidation reduction is two choices. So that means something has no change in terms of losing or gaining electrons. Has a reaction happened? Yes. But in terms of what's happening with the electrons, two substances will be more important, I guess, than the other one. Okay, so what you can do is help yourself and simplify things and write down what you already know. So right here, this oxygen all by itself, right away, you can label that as 0. And how we label that is in the top right-hand corner, just like a normal ionic charge, okay? Okay, so that was in our list of rules. That was the first rule. So then I would just keep going with the rules. So the other rule was, or other two rules we're going to use here. Hydrogen has to be +1 when it's in a compound, and oxygen is -2. So let's use those. Okay, so this is from the slide that says rules, okay? Oh, I didn't write it in though. Okay, so a couple of things. Now all we're left with in this compound in CH4 and in CO2, we are left only with carbon to figure out. Excellent. We only want one unknown. Oxygen, this elemental oxygen, we're done with. And now this compound, we're also done with. Combustion is nasty when you balance regularly because of the two oxygens. But if you notice, or two spots with oxygens, they are the same. Okay? So that means that on the product side, either oxygen is -2. So it started as 0 and went to -2. That is a change. So we have to figure out, did it lose or gain electrons? And then hydrogen, did it change? Here it's +1 and here it's +1. No, it didn't change. So that's good because we can't, there's no redox, there's no reduction, oxidation, and half oxidation or whatever. Two of them have to change, and we said that one couldn't. So we just showed that hydrogen does not change, it stays -1. So then we can stop thinking about it, okay? This is terrible handwriting. I'll fix that. Sorry. It doesn't really matter if you analyze oxygen first or do the solving for the carbon first. Maybe you could think about oxygen first and then check carbon to kind of check your answer, because if we decide that oxidation occurs with oxygen, then reduction has to be with carbon, or vice versa, right? So you could do it that way. So yeah, maybe I'll do that. So let's look at oxygen because we've already assigned the numbers. So you have to decide which way you like to think of it. It went from 0 to -2. That is more negative. That's a decrease in oxidation number either way. So becoming more negative or gaining electrons is going to be reduction. So that can be annoying because wouldn't it be nice if oxidation was oxygen? Sure would. But because of oxygen's high electronegativity, then it often is the substance that's reduced or gains electrons. So you can, in this situation, decide how much room you have left, because technically we just solved for carbon in CO or CH4. It was -4, or you can write it out again. We did not solve for carbon in carbon dioxide, so I'm going to write that first and see how much room I have left, okay? There we go. So we're going to apply the rule. Oxygen is -2 in a compound. Is +4 a possible charge for carbon? It sure is. Okay? So I'm going to label that up here. I've got some room here, so I'm gonna sneak it in again. But again, if you're out of room, we already did C in CH4 on the other slide, so you could just write it down. Okay, and that's really, we can use this and do it and sort of ignore what we chose over here and then make sure it works. So it went from -4. Oh, I wrote positive, sorry. -4 to +4. So that's an increase in oxidation number. It got more positive or less negative, which means that it lost electrons or lost negativeness, which is oxidation, Leo, which matches what we got here. Okay, we already decided that oxygen was reduction. That meant that automatically carbon had to be oxidation, but we proved it too.